Finally, let's look at the case where the car is driving faster than the design speed and traveling at 90 kilometers per hour. What happens here? Well, if the car is driving too fast, it tends to fly away or skid up the bank. To prevent that, there must be a friction force pointing downwards to hold the car in place. To find the required coefficient of that surface, let's set up the free body diagram once more. Okay? Just like before, we start with the gravity, Fg, and the normal force, Fn. The key difference now is that the car is trying to skid up and fly off the bank. Therefore, the friction force must be pointing down the slope to hold the car in place, right? See how that friction direction has completely reversed compared to the slow speed scenario. In the second part, we have this friction force pointing upwards, right? Now in this third part, as the car is driving fast, the friction force is pointing downwards. Again, we need to set up the coordinate system, x and y axis. When we decompose the normal force and friction force, the component equations are the same as before. Okay, for the normal force, we have Fnx and Fny. This is the angle theta. This is the angle theta. So Fnx is Fn sine theta. Fny equals to Fn cosine theta. And for the friction force, this is the Fx component and Fy component. This is F, and this is angle theta. So Fx is F cosine theta, and Fy is F sine theta. Now let's find the net forces. Again, starting from y direction, the F net y equals to, we have Fny is pointing up, Fny, and then Fy pointing down, and the gravity Fg pointing down. Again, because the car is not moving vertically, we have the net force in y direction equals to 0, and Fny is Fn cosine theta minus Fy is F sine theta, then minus Fg is mg. Now we replace Ff to mu Fn. So we have 0 equals to Fn cosine theta minus mu Fn sine theta minus mg. Moving mg to the left side, we have mg equals to Fn cosine theta minus mu sine theta. And on the right side, I factor out the Fn. In the x direction, we have F net x equals to Fnx plus Fx. And notice that we have the addition here this time. Last time in case 2, we have the subtraction here. This is because this time the friction component is now pointing in the same direction as the normal force component. And they are working together to keep the car in the turn. F net x is the centripetal force Fc. So we have Fc equals to Fnx is Fn sine theta plus Ffx is Ff cosine theta. And Fc is mv squared over r equals to Fn sine theta plus Ff is mu Fn cosine theta. And let's factor out Fn on the right side. So we have Fv squared over r equals to Fn sine theta plus mu cosine theta. Again, just like what we did, we simply divide equation 1 by equation 2, right? So we divide the equation 1 by equation 2, we get, on the left side, we get mg divided by mb squared over r equals 2. And on the right side, we have fn cosine theta minus mu sine theta over fn sine theta plus mu cosine theta. And this let us cancel out the fn and the mass m. Now let's plug in the values. Remember, theta is 12.1 degrees. So on the right side, we have cosine 12.1 degrees minus mu sine 12.1 degrees divided by sine 12.1 degrees plus mu cosine 12.1 degrees. And on the left side, we have the gravitational force is 9.8 meter per second squared divided by the speed. Again, the speed is 90 kilometers per hour. And dividing this number by 3.6, we convert it to 25 meter per second. So we have the speed is 25 meter per second, then squared, then over 180 meters. The calculation of this left side works out to 2.82. It equals to, on the right side, cosine 12.1 degrees is 0.98 and sine 12.1 degrees is 0.21. So we have 0.98 minus 0.21 mu divided by 0.21 plus 0.98 mu. To solve for the coefficient mu, let's get rid of the denominator first. So we have 2.82 multiplied by the denominator, 0.21 plus 0.98 equals to 0.98 minus 0.21 mu. Then we remove the bracket. 2.82 multiplied by 0.21 is 0.6. Then plus 2.82 multiplied by 0.98 is 2.76 mu equals to 0.98 minus 0.21 mu. And combining all the terms with mu, we get 2.76 mu plus 0.21 mu equals to 0.98 minus 0.6. Then on the left side, we have 2.97 mu equals to 0.38. So mu equals to 0.13. All right. After all that calculations, we find that the car driving too fast at 90 kilometers per hour, the required coefficient of friction to prevent it from flying off the road must be approximately 0.13. All right, there you have all of it. Now you should know how to analyze these different scenarios and solve for the forces when a car is turning on a bank curve. You should correctly determine the direction of the friction force, and deciding this friction is pointing up or down the bank is what lets you set up the correct equations every single time.